Okay, in this video, which is the 10th video in the playlist that deals with Lewis formulas, what I want to do here is practice drawing some resonance formulas with the viewer. So again, resonance is a situation we have when there's more than one equivalent structure possible for a particular molecule. So as a model, what we want to do first, and in the last video we did nitrate, so what we're going to start out with here is carbonate, because this is another classic model that you see in the textbooks and so on. So let's go ahead and do this one. All right, and we'll follow through the steps. Here's what we're gonna do. We're gonna blatantly follow the steps, and that's gonna lead to an initial structure that's wrong. And then I'm gonna modify what we do. And the key thing that you need to remember here that I may have forgotten to mention in the last video is that when we end up with a structure that has more valence electrons in it than the magic number, producing or utilizing a multiple bond like a double bond will reduce that number. So keep that in mind as we go through this. So carbon is in group 4, so there's 4 valence electrons for that. And then we have 3 oxygens, which is out of group 6, and our charge is -2, so we need to add a 2 on for that. The grand total is 24 electrons, which was similar to the situation with nitrate. All right, so we have 24 valence electrons that we need to use up. All right, and what I'm going to do next is get my skeletal structure, so I'll put the oxygens around my carbon, and the next thing that we're going to do is go ahead and connect. We're going to bond everything up. So here's a bond, and a bond. And then following the rules, we would start with unshared pairs so that carbon has 8, and then we would move out to the next atom out, putting in pairs of electrons so that these atoms have 8. Okay, and we end up with, okay, the structure visually looks pretty decent. So let's do our count. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So the structure is wrong. All right, now let's go ahead and we'll redo it. So here's my carbon, here's my oxygens. All right, whoops. And I'm going to go ahead and double bond up one of the oxygens. All right, and we'll go ahead and get the bonding done with the other ones. All right, and put in our unshared electrons, unshared pairs. I'm just going to fix this bond so it's more clear, like that. All right, and then we need unshared pairs here. All right, now let's see what we got for our total electron count. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. All right, so we hit our magic number. Now, quick inspection, we see that there are 8 electrons in all the key atoms here. All right, good news. Now, check it out. Like the situation with nitrogen, we could have put this double bond in 2 other locations. And to emphasize that fact, I'm going to go ahead and number my oxygens. So this is oxygen 1. This is oxygen, we'll make this one oxygen 2 and oxygen 3. All right, so in the new structure, I'm going to have a single bond going to oxygen number 1. And we'll have a double bond going down here to oxygen number 2. And a single bond going out to oxygen number 3. And we put in the pairs of electrons appropriately. We see that we have a new structure, which is essentially identical to the first one. But it's equivalent because you see the double bond is actually going to chemically different oxygen. All right, and then we're going to have our last structure, and the double bonded oxygen will now go to oxygen number 3. All right, and again, put in the pairs of electrons, the appropriate number. And there's a total of 3 resonance structures for this particular molecule. You know, and remember the deal is here is that the electrons involved in the multiple bond are being delocalized over the surface of the entire molecule. So none of these bonds actually are double bonds. A fraction of the electron density exists in each of the carbon-oxygen relationships. All right, now let's quickly look at another molecule. So I'm going to draw a line around this so that we can separate what we're going to do next. So maybe the screen will look a little bit less cluttered. All right, so let's take a look at phosphate, and we're going to combine some concepts now. So this is going to be like the sulfate example. So the first thing we're going to do is we're going to draw this structure of this abiding by the octet rule. So let's go ahead and get our valence electron count done. So we're going to have phosphorus is in group 5. So there's 5 electrons. Then we've got 4 oxygens, and oxygen is out of group 6. All right, and then we've got a total of 3 negative charges. All right, and that gives us a grand total of 32 electrons. So 32 electrons is the magic number for the phosphate molecule. All right, now since we're going to abide by the octet, well, this would be true even if we weren't. But all right, the next step is to draw the skeleton structure. So I'll do this. Phosphate's going to be my central atom, and we'll go ahead and deal with the bonding through the steps. We're abiding by the octet. Unshared pairs, now the phosphate is already a done deal, right? Because you can see that there's 8 electrons around it. So we come in and we put the pairs of electrons on all of the oxygens. Maybe not the prettiest thing in the world, but all right. So now let's go ahead and count up. And you see we've got 8 electrons around each oxygen set, and there's 4 sets. So actually, this structure, the way we've drawn it, see, it meets the magic number rule. And there's clearly 8 electrons on it. So what could possibly be the problem? All right, if we look at the formal charges, remember from the sulfate example that oxygens that are single bonded with 3 unshared pairs of electrons are -1 for Fc. But let's go ahead and recalculate it. So it's going to be, remember that it will be the total valence electrons of this specific atom. So it's going to be 6 minus, and then it's going to be quantity 1/2 the bonding electrons. Well, there's only one bond between the oxygen and the phosphate, or excuse me, the phosphorus. So that's going to be 1 electron. And then that's going to be added to the total number of electrons in unshared pairs. So it's going to be 2, 4, 6. So the formal charge on the oxygen is -1. That means that all of these guys are -1 because every single one of them is a single bonded oxygen, which means that the total net charge for all the oxygens is -4. All right? That means the charge on the phosphorus needs to be +1 in order for this thing to sum to the net charge that's on the polyanion, which is -3. But just to show you or to prove it, we'll calculate the Fc for the phosphorus. All right, so the total valence on the phosphorus is going to be 5. It's in group 5. And then it's going to be minus, all right, the total bonding electron count. So it's going to be 1/2 of the total bonding electron count. So it'll be 2, 4, 6, 8. So half of that is 4. and then it will be plus any unshared electron, the total number of unshared electrons, which is 0 in this case. So the formal charge on the phosphorus is +1. All right, now let's see if there's an alternative to this. And like we did in the phosphorus or in the sulfate example, I'm going to redraw this now, but this time what I'm going to do is add a double bond. All right, and I'm going to go ahead and come in and I'll put in my electrons. Whoops. No, that was right. Sorry. All right, put in my electrons. All right, and now we'll calculate formal charges. Now, we already know that the guys that are single bonded oxygens are -1. So I'm going to go ahead and put those in. We already know this. And we did this in the sulfate video, but I'm going to calculate the double bonded oxygen really fast. So it's going to be, FC is going to be 6 minus 1/2 of bonding, so it's 2, 4, divided by 2 is 2. All right, and then this is going to be added to the total unshareds, which is 4, and so the FC is 0 for this oxygen. All right, and that just leaves us to find the FC on our phosphorus. So we go ahead and do that, and the FC for that is going to be equal to 5 minus quantity. All right, we've got 2, 4, 6, 8, 10 electrons. Half of that is 5, and then there are no unshared pairs, so that's 0. So you can see the FC is 0 on the P. So this is actually, the structure that we have here is actually the correct one. All right, or I shouldn't say correct. I should say it's the best structure of the options. And if you want, you can go on and prove this to yourself. If you move to the next one with another double bond in here and then calculate it, you're going to find out you're going to move away from where FC is 0 for the phosphorus. Now, I'm going to number these oxygens. We're going to call this oxygen number 1, this oxygen number 2, this oxygen number 3, and this oxygen number 4. Now check this out. We could have put this double bond in any of these other 3 locations. So for this particular molecule, there's going to be 4 resonance structures, a total of 4. All right, and I'm going to write them very quickly down here. So here's one of them, and I'm going to leave out the unshared pairs of electrons in order to be efficient with time. So here's one. Here's the next one. All right, here's the next one. Each of the oxygens is chemically different. So I'm not just rotating the molecule. I'm actually putting the double bond in 4 different locations. So you can see that we've got a total of 4 resonance structures. For this particular molecule, for the phosphate, 4 resonance structures. So that just means that the electrons that are involved in that double bond are delocalized over the surface area of the whole molecule. All right? And with that, I'm going to go ahead and close.